Uh, right. So, welcome all of you. This is the 10th session and on the problem solving the 10th problem solving session. I'll just share the screen. Are you able to see my screen?
Yes, sir.
All right. I'll just pause this one. Yeah. All right. This is Vijay Rahane. Today we are here to solve the problem based on the course one and two dimension inverse spectroscopy for the chemist. And as of now, we have already seen the all the 1H NMR spectroscopy as well as the 13C. And we are slowly moved toward the two-dimensional NMR spectroscopy here. And in the two-dimensional NMR spectroscopy, so why this two-dimensional NMR spectroscopy is one of the important technique for the chemist in day-to-day life. So why it is important? So I will give one example from my experience. So this is the one of the my molecule, and I have synthesized this molecule. And after synthesizing, so I got the 1H NMR spectroscopy spectra for this one. So I will just show the 1H NMR as well for this molecule. So yeah, right. So this is the NMR spectra for the molecule that I have shown earlier. So this is the structure of the molecule. Well, again, control. Right. So this is the structure of the molecule, and for which I have taken the NMR spectra. Then, if you look at the structure of this molecule and try to get check the signal which are observed in the 1H NMR spectra. So here, so which is the distinct peak that we can easily analyze from this one. So if you look at the molecule has the one OH group, right? Sorry, two OH group. So which is here. So this OH, this proton, and this proton. So this proton is like a kind of a hydrogen bonded proton, right? So if you look at the structure of this molecule, in this one, so here there is a nitrogen and one is sulfur, and to which adjacent there is one phenyl ring, right? So and this is the OH. So actually, this proton present in this manner. So because of this, this NMR spectra, this proton lie well in the d-shielded zone. So this proton is observed here around 12 ppm. So if I have here the zoom cross section of this one, and if you look at this one, so which is lie around 12.6 ppm, right? So can you identify another any distinct peak which belongs to you can easily assign the peak. So if you look at in alpha region, this is one peak due to the four hydrogen. Here also there are uh, signal due to the 12 hydrogen, and here there is another signal which is due to around 10 hydrogens, right? So can anyone tell which is the distinct peak here? So can anyone tell which is the distinct peak in this one? So if you look at this C6H13, so this C6H13 stands for these alkyl chains, a linear C6H13, CH2, CH2, further CH2, CH2, and again one CH2, CH3. So like this way, right? So and this attached to the this fluorine. FL, that this fluorine in between, right? So this adjacent CH2 is around shows about 2.1 ppm, right? So which is of the 4 hydrogen. So we can easily assign this one as well. So already we have assigned this one. Also we have assigned this one. So and also if there is there are so I'll just highlight which we have assigned. This is we have assigned, right? Now we have to assign this CH3 and this CH2. This combine this peak shows here in this region. So which signal gives due to the 10 hydrogen. So there are two such groups, right? There are this is one, sorry, this is one, and again here two, right? So there are two groups. So we observe the signal here due to the 10 hydrogens, which is due to this terminal CH2, CH3. And what about the in between CH2, CH2, and CH2? This in between CH2s, they are lies shows signal of the 12 hydrogen around 1.24 ppm. So we have assigned this many peaks, but what about the remaining peaks? So to get the to assign what are the remaining peaks belongs to which hydrogen? So we need to take the help of 2D NMR spectra. So I have just recorded then the 2D NMR spectra, and in the 2D NMR spectra, I observed what I observed. So in this molecule, which peak is like shows the shows the singlet. So if you look at this signal, so this peak will show the singlet with the very singlet, or we can say the doublet with a very less coupling constant, which is in the NMR spectra. If you zoom here, so this signal, which is about 7.96, is you can see that due to the this hydrogen, which is weakly coupled with this hydrogen, which is at meta. So that's why I assigned that signal as the hydrogen of this phenyl, right? And later I just check the coupling. Sorry, I just missed that, not that one. I'll just check. Yeah, so this green hydrogen. So this green hydrogen I have assigned for the proton, and also this green hydrogen, which is linearly, if you look at this two, this is the Cauchy spectra, and in the Cauchy spectra is observed each corresponding to the straight line, we observe another signal. So which is for this proton. So it means this proton and this proton. Also, this proton also, if you look at here, there is also weakly coupling is observed, and this signal here. So this proton is come from one type of system. So here, if you look at this hydrogen, and this hydrogen. So this hydrogen is kind of AB system, right? And here there is weak, another coupling observed between this HA and HB, right? So in between this HB and this H, this system is a kind of HX system. So this is to all are in the correlated to with each other, right? So if you look at this one, this spectra is this signal is correlated with this one, right? And also which is correlated with this. You can see here signal is observed here with this one. So it means this proton, and these protons, they came from one type of system. And if you look at this splitting pattern, there is one doublet, right? Another also one doublet. Uh, Doublet of doublet, slightly the very big coupling. We call it as in the aromatic region. It will be the mostly the meta coupling, right? Doublet this due to the ortho coupling, and also we observe one small doublet with the very low coupling splitting, and which is also due to the meta, right? So sorry, this meta plus ortho, right? So it means this hydrogen, this hydrogen and this hydrogen, they are coupled with each other, and this hydrogen will show the doublet or doublet with definitely with the hydrogen which is the meta to this proton, right? So I will just highlight with the red color here, or the pink color. So this hydrogen will be the this doublet of doublet kind. So I just assign this hydrogen as a this, I will just label it as a H star. This signal due to the H star. Again, I observe one another doublet here, right? So this doublet. So where this doublet come from? If you look at this doublet and this or doublet of doublet is correlated with each other, right? It means they are adjacent to each other. So this hydrogen is belongs to this H star star, right? So this is then I have referred this as a H star star, right? So this signal is due to the this proton, and also the signal here, which has the doublet with very low coupling constant, or the doublet due to the meta coupling, that kind of. So this signal is comes from this H. Let's take X. So this signal comes from HX. So this is how we have assigned all the signals in the NMR spectra. And again, whatever the remaining signals are there, also did the same. Because if you look at this one, so in this blue type of system and the red type of system, the triplet, right? The triplet present for this hydrogen as well as this hydrogen, but no any triplet will be observed for in between system, because there are three type of protons, one, two, three. But this should be the doublet. This is also the doublet, doublet of doublet, because there is will be a some slight meta coupling, and here this will be doublet with this very small splitting or very small J value. But there is no any triplet, right? But if you look at this red type of red phenyl ring, which will have the triplet and the triplet. So whatever the whichever the triplet observed in the NMR spectra, if you look at there, so if you look at carefully, this is one triplet right here. So I just started from taking correlation from one signal. So I have just correlated this one. This one belongs to the this signal belongs to the just wait. So I just started from one of the triplet and extended this one. So here I'll just rub all the remaining. Right. Then I started from one of the signals. Let's start. This should be the doublet. This should be the triplet. This should be the triplet, and this also should be the triplet, right? So here in this one, so which triplet here will be the so if you observe, this is the doublet. This is also a doublet. This one is also a doublet. This is doublet of doublet. Here is the it is doublet. Here one slight singlet or doublet. We can say doublet, and again this in between there will be a triplet, right? So when I started from the from showing correlation from one signal, so we just correlate started from one of the triplet, and let's take this triplet. This triplet also correlate with the this signal. Again, this signal also have some correlation here as well as sorry here, and which again show correlate with this one. So in this way, we can check whichever the addition proton present here. Just we need to go identify at least one of the signal belongs to which. And if you look at the then why after assigning, if you look at the data, so we have assigned all the signals from this one. This is the supplementary from one of the manuscript that I am writing right now. So here, right. So here, if you look at this one, the signal. So each and every signal that I have assigned. So this signal at the 12.6 6, it comes from two hydrogens of the alcohol proton. Also signal at 8.04, which is doublet for the two hydrogens, and this come from the benzothiazole hydrogens. Also later signal at this 7.96, which is the doublet with the splitting very small, which is due to the phenyl that I have shown the phenyl hydrogen right here. So this phenyl hydrogen. So in between there is one phenyl, right? So this phenyl hydrogen. Again, all the hydrogen, this hydrogen from the benzothiazole, that benzothiazole in between. So this entire this called as I call this as a benzothiazole. So this benzothiazole system. it comes from benzothiazole. Also, if we look at the aliphatic region, in the aliphatic region, the signal at the 2.13 to 2.05 uh, due to the 4 hydrogen, which is multiplate, and that comes from the CH2 group, which is attached to the fluorine. Also, there will be another multiplate of the 12 hydrogen because of this CH2 in between that CH2 groups, right? From the chain, there is C6H13, right? So 1, 2, 3, these three is in between. These 12 hydrogens comes from that chain. And also there is a multiplate of tail hydrogen, which is from the this CH2 CH3 terminal group. So in this way, you can able to assign all the signals by using the 2D NMR spectroscopy. So uh, this is the example of the cozy NMR spectra of this molecule, and by using this cozy NMR, we can able to solve the complex problem like the assigning the signals in the 1H NMR spectra. So also we can see there are multiple example that I have shown. So we need to get the first 1H NMR spectra. So let's take the simple molecule. Uh, I think for this one, I have not shown the 2D NMR spectra, but whichever the molecule which are like uh, difficult to assign the signal of each and every version, we can able to assign by using this 2D NMR spectra. So here also the same example, the molecule is also almost same, only instead of fluorine, here it is carbazole, and which has this hexyl chain. In between also there is like benzothiazole group, phenyl ring. This is the carbazole. So all the protons that assigned by using by with the help of the 2D NMR spectra. So just started from one signal. I have just identified which have this doublet. This is the doublet of doublet, and this is the doublet. This doublet with the one J value around 8 hertz and another J value about 2 hertz, right? Then this has the J value about 2 hertz. This doublet with the J value about 8 hertz. So I have identified this pattern. So there is three signals in this molecule, which are comes from one type of system. And then same in the same manner, I will just give for one example. So I have started from one proton, which is correlated with another, and in this manner, I just correlated all the signal. So what does it indicate? It indicates this signal come from which protons. So in this cozy NMR, the adjacent signal, we observe the signal uh, in this manner. So we observe this signal, and this signal we can able from this signal we can able to correlate adjacent protons. So this is the example of the why the 2D NMR spectroscopy is important in the day-to-day life of the chemist. So any doubt in this 2D NMR spectroscopy, whatever the topic that covered by professor in the week 10 videos? All right, if you don't have any doubt, we'll directly move to the today's problem. All the problems are based on the direct statements. So I will not spend much time here. So in the first problem, it is like mentioned in a regular coupled ion EPT experiment, the application of 180-degree pulse in both 1H and 13C with the fixed delay before and after the pulse helps in achieving the 1H decoupling uh, in the signal. So the option here is the 1H decoupling. In the second problem, what should be the delay in regular ion EPT experiment to detect only CH carbon with positive phase and the maximum intensity? So for this one, which is the value should be equal, the delay should be exactly equal to 1 by 2 of the J value. So sorry, 1 by 2 of J. So that much delay we need to give to or detect the only CH, not CH2 or any CH3, that kind of signal. In the third question, in the NOE stands for nuclear overabsorb effect, right? Which you have already seen the videos. In the NOE enhancement between two nuclei, I and J, separated by distance r, is related by the terms. So for this one, the formula is 1 by Rij raised to 6. This is the formula for this one to identify the the NOA enhancement. So this is the relation. The option C is the correct option here. The next question here is given in the INEPT experiment. If CH2 and CH3 carbon have to appear with positive phase, then the delay delta has to be set to. So for this one, a note given is like Jij is the one bond coupling between the 1H and 13C spins. So in this one, so it should be the 1 by 4 of 4 Ji. So Jij. So this is the option A is the correct option in this one. In the next question, so if this is kind of multiple selective question. So in this one, if the molecule contain abundant spin like 1H and the F19, abundance in terms of natural abundance of the NMR active nuclei, and the less abundant spin like 13C or nitrogen 15, then in INEPT experiment can be used to INEPT experiment can use to transfer magnetization from 1H to the 13C or F90 to the F19 to 13C. Also 1H to 19F and F19 to the 19F. So you can able to transfer the magnetization by using this INEPT experiment. So the option 1 and 2 will be the correct option in this case. For the next question, the major source of interaction responsible for the NOE advancement is the dipolar interaction. So this is the major dipolar interaction is the major source of interaction for which is responsible for the NOE. In the another case given, so in the NOE, so another question given in the NOE experiment, if the spin followed zero quantum relaxation pathway after saturation by a weak RF, then NOE enhancement would be, so it will be a negative values if it is weak RF. If it is saturated by weak RF. In the eighth one, in the eighth question, in an NOE experiment, the signal enhancement depends on. So here, all the above are the correct option. All the above here, because here the it also NOE also depends on the molecular mobility, that is correlation time TC, also the Larmor frequency, and again also the various pathways available for relaxation. So this NOE signal in the NOE experiment, the signal enhancement depends on all of these factors. So A, B, C, all these three you need to take. In the ninth question, the spectral density function JW depends on the motion of the spin and the Larmor frequency. So option D is here is the correct option. And in the last question, if the signal uh, if the single quantum relaxation pathway W1 is highly dominated compared to the double quantum relaxation pathway W2 and zero quantum relaxation pathway W0, then NO may not be there. So this is the option for correct answer for this 10th question. So these are the some question from directly I have taken from the assignment. So if you have doubt any regarding the how the NMR instrument uh, regarding the 2D NMR spectra, that also we are going to see in the week 10 video as well with the some other example. So anyone have any doubt here? If you don't have any doubt, we'll stop here for today. And in the next video, I will get more example of this 2D NMR spectra. And uh, in the same manner, I will show the 2D NMR spectra in terms of 2D, which is like what are the general way to we took the 1H 1H coupling, so sorry, correlation spectroscopy. We call it as a COSY, right? Also, we took 1H and 13C, that sort of experiment. I will also show some the spectra of these DPT, how the DPT looks like. DPT is, I mean, not much difference between the 13C and the DPT. Only in the DPT, there will be the signals in the negative direction. So if you look at the DPT 135, so in the DPT 135, there will be signal in the negative direction. Some signal will be in positive direction in this manner. And this is from the 0 to, let's say, about 200 ppm. And we observe the signals in the negative as well as the positive direction. So in this manner, we observe the signal in the DPT 135. So this is the difference between DPT and the 13C. There is not much major difference, but I will show some spectra for this DPT as well as the COSY or the 1H13C, that kind of correlation spectra. So we'll stop here for today. So if anyone have any doubt, please let me know.